He joked at the beginning that I might start preaching in here, and I very well might. There are a few topics that get me as excited as the 5G/4G world and bridging that last mile connectivity problem. All of us in here have a shared goal and a shared purpose, and it is delivering that connectivity experience between people and the experiences that matter to them. And that is our ultimate goal at Alabama Lightwave. So by means of introduction, I'm Josh. I'm the CEO of Alabama Lightwave. My background is not networking. My background, as I mentioned, is software. I kind of got dragged kicking and screaming into this world because the network options in my town did not work. And I had to solve this problem in order to do my job. So delighted to be here. Probably not as smart as you guys in here, but hopefully have enough information to try to keep up. So one of the most exciting software projects that I've been working on as of late is called Rapid 5GS. What Rapid 5GS is a magic wand. It is a way to quickly get online a mobility core to support 5G and LTE deployments. So what we're going to do is this project, this lecture, is going to give you a speed run, a literal speed run education of how LTE and 5G works, where a packet core fits into that world, why it's important, and why we need it to bridge that last mile connectivity gap. And by the way, I believe this technology is the linchpin that is going to underpin the AI we've been buzzing about the last 2 years. 5G, 4G is how these devices are going to get online. Honestly, maybe I should have titled the talk Networking the Skynet, right? Because that's ultimately what this is going to do. We're in the middle of seismic shift here when it comes to networking. I do want to point out that everything in here is covered also on at joshlambert.xyz/rapid5gs and the website rapid5gs.com. Let's get started. So first thing we're going to do is set the stage. Why is this topic important? Why are we concerned about 5G and LTE? Across the country, we're seeing a growing need for resilient and, more importantly, locally owned and controlled connectivity infrastructure, right? It's like I hinted at earlier. Right now, everything has been built in these regional hubs, and all the buzz is about moving this stuff to what they call the edge. We're getting it as close as possible to the customer, where we can deliver them the lowest latency and the most speed to underpin this AI revolution that we're in the middle of experiencing. Now, whether you're like a rural school district looking to get your buses connected for whatever AI application you're going to deploy there, maybe you're trying to detect fights breaking out in the bus or something like that, right? Whether you're trying to solve for a problem like that, or you're trying to solve for getting broadband into a community where fiber is simply not financially doable, or perhaps you're trying to deploy your own voice over LTE to power telephone services in an area with inadequate cell coverage. 5G and LTE solves all of these problems. It is a mature, hardened, and believe it or not, as I will prove today, cost-effective way to solve these connectivity challenges. You actually don't need grant money to get this done, as we have proven in Bibb County, Alabama, Chilton County, and Choctaw County. So you would think about it to power things like a hospital for all the Internet of Things devices that run inside that building. They can communicate over LTE, which is a secure, hardened way to communicate. When you think about how wireless networks normally work, you're used to this idea of picking a network, putting in a key, you connect to the network, off you go. Lots of problems with this model, right? Someone can copy the password, somebody can spoof the connected device. LTE solves these problems by giving you a SIM card, which has your private key on it to connect to the network. What that means is that your identity on the network can travel with you across devices and get you online in one of the most secure ways possible. This is why industries like oil rigs, hospitals, the Department of Defense, they rely on these technologies to connect the services that keep us safe and healthy. 5G and LTE is how those problems are solved. The challenge, though, is that deploying these networks historically has required substantial capital investment, an unbelievable amount of domain knowledge, heartache, lost sleep. You're trying to keep up, you're trying to marathon through Seinfeld and watch every episode 1 week or watch the entire Lord of the Rings. Good luck, because you're going to be spending your whole week in your packet core or in your RAN hardware. It's not fun. So the goal is to take all this complexity that we're about to look at and distill it down into a way that any of us could deploy our own LTE network in our backyard on a Saturday. And I'm about to show you this is possible right now with technology that exists today. And at the heart of that is the packet core. So traditionally, when you think about networking, you have routers and you have switches. You really can boil it down to those two things. Routing, telling your traffic where to go, switches, bridging these different devices together. LTE runs, and 5G runs over the top of that, and it enables that rich connectivity experience we talk about. So it's not an either-or thing, it's a both and. You build resilient networks like you guys in this room are doing today, and LTE runs over the top of that to deliver that connectivity experience. So to deploy those complex and rapid 5GS, its goal is to solve that problem rapidly. So let's take a look at how that works. So first question we're going to get. Why would I not just deploy Wi-Fi? And the thing is, in many cases, Wi-Fi is actually the right answer. May blow your mind saying that. Here I am giving a talk about 5G, and I'm telling you no, just deploy Wi-Fi. Not every site justifies a full mobility core. So we're actually looking at a real site here. This is Macaulay Hill up in rural Bibb County, just north of our wildlife refuge and just north of the Okmulgee National Forest. This site is in the middle of nowhere. The reason that this site exists is in support of this WBRC weather camera. There's like 15 rooftops in the immediate vicinity of this house. It's way away from traditional fiber, and it is in range of a planned cell site. So with these things in mind, with our mind of putting an actual cell site to cover this 5 miles away, there's absolutely no reason to do an LTE deployment here. But we did need this camera, and we figured it would be nice at the same time to connect the houses around it. So in this case, we didn't use 5G or LTE. It was the wrong tool for the job. We often talk about in the WISP world, we call it all the tools in the toolbox. This table over here kind of illustrates that concept. So we have traditional antennas here and traditional radio heads and appliances. We'll get into what these things do in a minute. But I actually have a mix of both technology stacks here. We have hardware used for traditional fixed wireless deployments, like this Cambium access point, this Mimosa C5 for getting internet to a customer location, this Cambium CPE. These are very similar devices to what was used in this deployment. You see we have our Omni antenna up top for distributing fixed wireless broadband to the people around here, our WBRC Macaulay camera, and our backhaul that connects it to a nearby site. No LTE here because the application didn't require it. Sometimes the smart calls to not use LTE, even when it's available. It's about engineering discipline, not dogma. Knowing when to use the right tools and not being arrogant to think you need a Cadillac to take your aunt to her medical appointment, right? The Corolla will do just fine. I happen to love them. All right. So before we get deeper in explaining the core, we have to speed run what LTE is. I have been struggling to condense down how it works into these basic components that we can rapid fire through so you can understand how the packet core fits into the 5G world. So it's best to think about it like a layer that, as I mentioned earlier, runs over the top of your traditional network. So we've got 3 pieces that we're going to talk about. You can think of these like categories. You have your core, your EPC/5GC. You have your ENBs and GNBs. That's the closest thing to think about them like would be like an access point. That's really the closest way to describe these to actually get into the network. Traditionally, that might be your fiber OLT or the wireless router in your home. These are examples of access points. And in the LTE world, we group these into categories called E node B and G node B. And then finally, you have your user equipment, which is UE. Now, this is where LTE really shines and 5G really shines. What we're dealing with here is not a proprietary standard, but an open standard, where vendors can come and go, device types can come and go, but ultimately they're all following the same rulebook, and that allows you to mix and match things in really unique and interesting ways, which we'll look at here in just a minute. So we have the user equipment, and I define these as anything with a SIM card. So you all have 5G UE either in your hand, because I'm boring, or in your pocket, because you're really dialed in. Probably not that. You all have UE with you right now. And that can take the form of an antenna outside on your house. That can mean the phone in your hand, and it can also mean IoT applications. Like I have this Raspberry Pi down here, which you might use for telemetry, right? You can put a SIM card in there, and it is also UE. So you can see UE takes many forms. Then we get to what we call the RAN, the Radio Access Network. And that's your GNBs and ENBs. These are the appliances that you will see up on towers or on rooftops that connect the UE to your LTE network. So some examples of RAN would be like this 600 megahertz radio right here that can power a cell site covering devices 10 miles away. This is an extremely powerful, robust radio. We love them. We know people in the state that have them deployed. We are very jealous. We wish we had many of them. Other examples of UE are like this Bicell's 436Q, which is a good entry-level device to deploying LTE, or this Nokia AZQC for CBRS, which we'll talk about here in just a second. That makes up your RAN. And then finally, we have the packet core. And that really is the brains of the operation. It authenticates users into your network. It assigns them IPs. It determines how traffic moves across your network. So it actually operates above the routers you're used to, right? It's routing between cell sites, routing between cell cores. That level, the EPC controls all of that. You can almost think of it like an air traffic controller. So before we start pulling apart acronyms like MME or SGI, which we'll get into in just a second, this right here is the mental model that I want you to think about this talk in. Okay? It is not that complicated prior to what your, regardless of what your very expensive consultants tell you. You really can boil this down to 3 basic categories connected to your WAN, and you better be the MJMIX very soon. That's all this is. Very basic, very simple. So let's start with the RAN. We're going to speed through RAN. I'm going to give you guys 2 months of knowledge here in about 10 minutes. We're going to try to pack this in real quick. So starting with the RAN, we have a couple of different ways this can look, and I'm going to talk you through that. When you think about your cell tower, you think about a monolithic component, right? You connect to this tower, it gets your devices onto the internet. But depending on how you've deployed your equipment, that's not really a fair way to think about it. Your cell site is really a collection of components that operate together to get you online. So, and that architecture can vary, which I'll show you. So take Bicells, for example. We have a Bicells right here. This is a 436Q access point, part of the RAN. That device includes your RRU and your BBU in one box. So what those terms mean, RRU is your remote, try to get this right, not butcher it. That's your remote radio unit, or you'll sometimes hear them referred to as RRH, remote radio head. It's responsible for the transmission of, it's literally a radio transmitter, right? Zeros and ones to your devices. It's controlled by a BBU, and that's known as a baseband unit. The baseband unit tells your radios how they need to function, right? So you think about like what channels they're supposed to be on. You think about how we're going to handle when interference shows up. We're going to talk about what transmission power you're at. The BBU is responsible for those components. So when you're first getting started in LTE, a really easy way to start is to get the most basic RAN you can for that first piece of LTE, which is the 436Q. It does all of that in one box, and you can use this device, they're very affordable, to get an LTE network online. So let's explore this a little bit. Oh, and then we have the other architecture, which is a Nokia system. Nokia is the top class. It is my favorite of the LTE systems because you can get your mind around it. It's very robust. It's trusted by entities ranging from government all the way down to your small business and everywhere in between. In their model, you have a BBU that's down in the compound that is controlling your remote radio heads that are up on the tower. So they break the components out. The reason this is important is because 5G, unlike traditional Wi-Fi, can bond multiple channels together. So for example, if you have CBRS running in the 3 gigahertz world, and you also have, say, 600 megahertz spectrum, LTE has the ability to take these 2 discrete bands and combine them together. So rather than buying a unit that only operates in the 3 gigahertz, it's all integrated like that, you can have a single BBU in your compound that feeds a 3 gigahertz radio, a 600 megahertz radio, a 2.5 gigahertz radio, right? Wherever you have that spectrum, it can glue them all together into one cohesive data stream for maximum capacity. Wi-Fi doesn't have a dream of doing that. That is a 5G, 4G, 3G specific advantage you have. They just can't do that. So we have deployed both. There are use cases for both. And really your application is going to define where you want to use those. So let's look at our first case study. This is a real world example we're looking at of one of those Bicells units. What you see in the background is actually low income housing. So the challenge here was that these people blew us up, called us incessantly for connectivity. The problem is, as we mentioned, it's low-income housing. There's a lot of regulations that are over that preclude what you're able to do. We wanted to hang fiber. It could be done, but it's super expensive, lots of paperwork, permitting, stuff that for a small shop, very difficult to do. The other issue is that they didn't want us to mount anything on a customer house. That's another major limitation. If I can't put an antenna outside and I can't drill through the walls to put in fiber, my hands are very much tied with how I can get a community like this online. 5G, 4G can solve this problem. What we did here, this is a utility pole that's actually in the right-of-way. You have one of those bicells units up there on your pole. You have a sector antenna that's pointed at the homes there. So internet comes in, millimeter wave internet, comes in on this backhaul and is distributed to the customers in a small cell fashion. What that means is to get people on the network, all you have to do is give them one of these and they can get online. This box right here picks up the signal from outside on the street level and creates a Wi-Fi network in the home they can connect to. No drilling, no permits, no landlord involved. Put one of those outside, you're off to the races. I'm gonna ask our construction partner here, how long did it take to build this one that we see here?
Day and a half.
Day and a half. Guys, it's a record. You cannot bring communities online that quick any other way. Like, I challenge you, try to do it, you can't do it. 3 guys, a bucket truck, and a day and a half of work. We pass, I forget how many doors it was, 60 doors?
67.
67 doors, 67 doors. You wanna talk about bridging the digital divide? There you go. So that's on your pole, that's in your customer home. The beauty of LTE is that you don't need all this equipment necessarily at each location. This is an actual picture of what's in the cabinet at the bottom of this microcell. So real basic. You have your router here, a MikroTik hex PoE that's doing the routing functions at this site. You have a fiber switch here for breaking out the devices that require fiber connectivity. And you have Ethernet surge protection. We pre-assemble these at our warehouse. And so the build is literally go out there, mount the sucker to a pole, pull your Ethernet up to the top, plug everything in, aim it, connect your electrical service, and you're done. It's like manufactured housing meets internet. It's honestly crazy. So we can also be real precise about how things are set up in there. Really good quality control, which is important for delivering good connectivity. That's your small cell. The next example is a macrocell. So this is a real LTE site that's out in the wild right now. Up top, we have a water tank here. You can see our big sector antenna, like that one right there. We can see one of our radio head units, like we just talked about. That's your transmitter. Cabling runs down from the top of this water tank into this compound where it hits the BBU, that device we just talked about that's telling those transmitters how to function. So when you're trying to do broad coverage, you do something like this, right? This is for covering, I want to say our cell radius on this was 5 miles. You can add a little more or subtract a little more based on your terrain. If you're up on a pole, if you're in a tree, you can get bandwidth to people in places where it's hard. But this is just CBRS, 3 gigahertz. It's frequencies that anyone in here can use. You can reach customers through trees using this setup. So our BBU that's on the table, you see it right there. Those fibers go to the top of the tank where they connect to our radio heads and ultimately get these customers to the internet. So your traditional routing is up there. You have your power control here. You have your DC rectifier here, your battery here, and that's your whole cell site in a single rack. And then we have our packet core, which probably going to get some looks on that one. That's a thin client computer, basically, that's running the brain of this site. And we're going to get to how that works here in just a second, because it's honestly crazy. It's one of these right here that you can buy on eBay right now for $65, operating as the packet core for the cell site. So we're going to talk about how that works here in just a second. So that's our cell site. And then we get to the core. So you'll notice what I didn't mention when I talked about RAN is the networking stuff that you would expect to hear. We didn't talk about authentication, getting users on and off the network, kicking them off when they don't pay their bill. We didn't talk about putting the SIM cards in the network so you know who these subscribers are. We didn't talk about setting what speeds they're able to get. We didn't talk about how they move between different networks that you might have roaming agreements with. RAN doesn't touch any of that. It's just transmitting data. The actual brains of the network lives at the core level. And traditionally, this right here is the hardest problem to solve. Cores are complicated. So I have it split out here into these different categories that make up how data moves, right? I'm not going to bore you with what all of these do. The point of this illustration, this was given to me by a veteran operator here in the state that has successfully deployed one of these, and I honestly couldn't draw it better. There are so many pieces in here that make this work. You have to plumb all of these components together, have them listening on the right ports, have them knowing how to talk to each other. It is a insane job, even if you know what you're doing, to get this right the first time. So those functions include things like getting the traffic out to the internet, your assigning of IP addresses, where we would traditionally do this with DHCP. The EPC or the 5GC is what does this function in the LTE world. Your home subscriber server, which is what's controlling what SIMs are allowed on your network. These are all different components you have to build and plumb. It is hard, very, very hard. Now, you don't need all of these features on day one. You're not building Verizon, right? Most of us aren't doing that. We just want to be able to get that insane punch that LTE gives us. So don't be overwhelmed by that. This is to make a point. Traditionally, that's been what you have to set up. And I wish you good luck. It is difficult. So, solutions to this problem. There are lots of commercial things you can buy that solve this problem. Be prepared to spend money. I heard one number, somebody spent $20,000 the other day, and you still then have to bring in high-powered consultants to configure it, just to start, before you connect the first customer. Very, very expensive stuff. And it can start, that's like the starting price. This gets exponentially more expensive when you start trying to do things like voice calls or roaming. These things get complicated quickly. Well, there are open source solutions that do that. Open5GS is a good example. It is a packet core that implements the different LTE components like the MME, the SGW. It implements all of these functions and does it well. The problem is you still have to get them plumbed together and appropriately talking to your RAN hardware to actually get anything online. It's a nightmare. First time I tried to set this up, it was like 2 weeks. So just hard hitting on this, plus a lot of assistance from AI. Because again, self-taught here. Very, very difficult to do this traditionally. But it is robust. You can build on this platform, and it works pretty well. Universities use it, research labs, small ISPs like us. It's stable, it's battle-tested, and it's still under active development. I checked yesterday. The most recent check-in of the software was 4 days ago. So people are constantly improving this core. But you do have the configuration challenge of setting it up, and that's where we come in. So now let's bring it all together. Rapid 5GS. This takes that complexity of plumbing all that together and makes it stupid simple. We take the excellent work done by Open5GS and we give you an opinionated deployment, meaning we go ahead and pre-configure everything the way we think it should work to get you online as quickly as possible and able to use LTE devices. Think of it as the friendliest possible door to LTE deployment. I like to think of it like this, right? You're going into Linux, you could be deploying Gentoo, which is really, really complicated, or Ubuntu. We try to be the Ubuntu of the 5GS world. Make it stupid simple. I don't want to understand all the complexity when I'm just trying to get online. Now it's still Open5GS. You can get into the core and configure it after initial installation, but you don't have to do that to get started. So part of seeing LTE more broadly adopted is dropping that barrier of entry, which is what Rapid 5GS does. It's got a lot of applications too. So this core, I'm going to go ahead and set some expectations now. You're not going to use this for doing voice initially. It's not configured to do that out of the box. This is designed for getting devices online. That's all. The only consideration we had here was making it as easy as possible to take hardware like this, put it in the air, and get devices on the internet. If you want to get more complicated than that, you certainly can, but that's outside the scope of what we're trying to do here. Our goals are make it easy to get online. So it starts with the one-liner install command. This is where my software background comes out. I am super lazy. I do not want to spend a bunch of time compiling programs, pulling in dependencies, configuring package managers. It's a nightmare. Personally, I'd rather watch my kids play soccer at the park. I don't want to get deep in the weeds. So Rapid 5GS gives you a copy button. You install Linux on your computer, just bare bones Debian or Ubuntu. You hit that copy button, you paste it into your terminal, and you hit enter. In less than 5 minutes, if you don't have crappy internet, you'll have a fully configured EPC without touching any configuration files at all. Copy the command, paste the command, hit enter. It's that simple. We targeted the two, what I think are the easiest to use Linuxes that are out there. We have Ubuntu. We also have Debian. I'm a big free software nut. I like Debian because I think it's a more pure Linux. So for my own gratification, I deployed it for both, but you don't have to do that. Just download Ubuntu, install it on one of these $60 mini computers, run this command, bam, you have an LTE core. It's that simple. Now, this isn't inside a container. This is not on a Docker image. This is configuring a bare metal appliance. You remember, I showed you one of these. These devices are so small, so tiny, so compact. I like this one because it has actual Phillips head screws you can take out, no weird bits to get in here and modify it easily. It runs on one of these, $60. A science teacher at a high school could buy one of these to teach their kids LTE, which is crazy to think about. You could teach your students how to deploy their own cell network because this is very affordable, right? We like these, but they're also small. This thin client can go inside the cabinet. So you could just put this in the cabinet at one of your microcells like we looked at earlier and not need to go back to a data center to get your LTE connected. That's one of the game changers. This can run distributed, locally, close to the customers, close to the edge, which is really important for AI. Basically, it's like installing WordPress. If you've ever done that, 5 minutes or less, this is a similar technical skill set you'll need here. Very simple. If you can install Linux, if you can run a command, you can get LTE deployed. So the program is really broken into two pieces. These are bash scripts. Yes, written in actual bash, not Node, not Python, not Java, bash. They're written in bash because it's the language you interact with immediately when you drop into Linux, meaning that I think for most people, you can actually pop this code open and read it. You can audit it. We talked about earlier during the AI test that, or the AI conversation, that people are constantly shifting the goalposts around with what they will or will not do with your data. I personally see that as a major problem, especially as this AI gets more and more integrated. On the way to your AI, though, is the network connecting them. And so if you don't know what's going on in that blob, you really have no idea who's seeing your stuff. Even if your AI is robust, if the core in the middle is not, it's not secure, even if they tell you it is. So if you're not built on something open source that you can look at, that you can see, that you can inspect, you can't trust it. Well, Open5GS, that this is built on, fully open source, as is this. We actually picked the most aggressive free software license, the GPL v3. Very aggressive to keep people from copying this, making it closed source, and improving on it without passing those changes on to you. This is as, I think, as pure, put this in quotes, as you can get for something like this. Communications, especially in an AI world, is so important. So it's written in bash, it's fully open source. You can look at it on GitHub. So what you do is you run that one-line install command, and you're presented with numbered options. You'll notice what you don't see here. You don't see read the manual. I hate that. It's so condescending. It's true, but it's condescending. Your science teacher that's trying to show kids this doesn't have time for that. So you run this program, and you key in numbers. Hit number 1, hit enter. The script's going to run and see if your computer is capable of running this core. Hit number 2. It's going to ask you questions, walking you through what you need to enter to network your devices. It installs the database, MongoDB. It installs Node.js. It installs the underlying Open5GS core. And it installs the web UI. You literally just open it, hit 1, hit enter, watch it run. Hit 2, hit enter, watch it run. Hit 3, hit enter, watch it run. All the way down the line with minimal training and basic Linux experience, you can set this up. It is rapid in the truest sense of the word. Now, again, setting some expectations. The wizard is going to ask you questions such as, what MCC and MNC number are you using? This is related to the SIM cards that you have on your devices. You can't just take a Verizon SIM card and put it on your network. That's not how it works. There are actually SIM cards that are specifically designed for amateurs deploying LTE that use the, 90170 combination of codes. So you will want to have a little bit of knowledge of that for your SIM cards, but this is very basic stuff that doesn't require you to know all that complicated plumbing. So then we move over to control. Once you get it online, the other issue is then looking at the health of your network. So traditionally with Open5GS, this means opening log files and digging through cryptic things. Even the timestamps, for crying out loud, are not human readable, right? When I'm looking at a log, I just want to know when something happened. If I had one of my EMBs go offline, I want the time. Don't give me an epoch time. Give me what time it was in Bibb County, Alabama, because that's the only thing that's relevant right there when I'm looking through it, right? When I say opinionated, that's what I mean. We're very opinionated about making it easy for anybody to look at, right? So we broke those out into components. You can hit one button and see how much data is going through your EPC. Check this out. I actually have a slide that shows that. So you see our two interfaces here that we binded. We have our WAN address, that is how the EPC communicates with the internet. We have our management address where the devices communicate with the core. And it's really cool because you can see here that our devices, they have data being uploaded to them, and you can see we have data coming from our WAN down to the core. So you can see data coming in and data going out. And this is real time. It's really aesthetic to just open this thing and watch. You can watch the little squares moving around in real time as data moves, as people are over there running speed tests, streaming Netflix. You can watch these numbers move around in your terminal to see that data is flowing through there, which is super cool. We have our ENB status monitor. So this is showing the different ENBs, these devices we talked about, your RAN hardware. We're able to immediately look and see human readable timestamp. We're able to see the latency, which is the time between our core and the end user device. This is where I have to give a shout out to the MGMIX again, because one of the early experiments we wanted to do was, if we put one of these in Jemison, can we bring an ENB online in Brent, passing it through the MGMIX? How will that work? And delighted to say it works. You can set up one of these in one city, jump across the IX and hit the other one, and have your LTE functionality either in the cabinet there by the customer or at your data center. And so this allows you to see in real time how far away those devices are, so you can correct issues if you have them. Tells you if your ENBs are attached or detached. So if one's in an error state, you can quickly spot that and fix it right from here. And the IP addresses. This is another thing where you don't necessarily get the IPs of the units that connect to your core. You don't know what they are without digging through log files. This solves that problem. Puts them all on a table where you can quickly and immediately see it. Getting over here to the UE status screen. This is another very helpful screen. So these are examples of customer UEs, user equipment, that's attached to our network. Our script is constantly parsing through the Open5GS logs to figure out what the IP address is of those UEs based on the LTE access point that they're attached to, the name of the access point. So your technician can run one command, get everybody attached to the box, and immediately get to the IP to control their equipment without digging through a bunch of logs and scanning stuff. All human-friendly, nice, easy to read date there, not military time, easy to read, you can immediately get to it. Then we have our, we call this the HSS. This is where we step back into the functionality Open5GS gives you by default. So we set this up in our script so you don't have to, and it allows you to quickly get in here and see all your subscribers. That's their MC numbers. I've got them blurred for the purposes of the presentation, but you can click them, immediately open them up, put in the private keys that belong to their SIM cards, as well as control the amount of data that they're allowed to get. So here we can set their traffic shaping profile to make sure they're not taking up all the data on your tower, and attach IP addresses to them here. So if you don't want it to just dynamically give one out, here is where you do the equivalent of static DHCP. So when you think about traditional routing, you give out IPs with DHCP. That's not how it works in LTE. The packet core assigns those IP addresses, and you control what IPs are going to what devices from that HSS function, which is what you see here. And once again, you don't have to add config files to do this. It's just a web UI. If you can browse Facebook, you can control this. Yes, sir?
Can they move, can they take their unit to like to a different place where it might have service on a different radio?
Yes, they can, and that's part of what makes this crazy. So with traditional fixed wireless, like that example we looked at with Macaulay Hill, those CPEs are attached to that specific access point. And for most fixed wireless equipment, that's how it works. Now, there are some exceptions to that. Cambium, you don't have to do that. So there are obviously exceptions to that rule. But most of the time, yeah, that CPE is paired to the local access point. And LTE, no. That's the beauty of one of these packet cores, is no matter what the access point is, no matter what brand it is, no matter if it's on a microcell or a tower, as long as that SIM card is registered properly to your network and the access points that you're using are attached to a central core like this, the core can instantly move it between those towers with ease without the subscriber having to do anything, which is magical. It reduces so much administrative overhead to be able to do that. OK, so here's where we're actually connecting a RAN device to Open5GS. So this is just a basic Linux IP ADDR command to see the IP addresses that are attached to my computer. And you can see right there on Eno1, we have that management IP that we specified when we set this core up. You simply take that IP, you paste it into your BiCells right there, you enter the PLMN, and you hit save, and then reboot the unit. And in less, what is it, Tommy, about 5 minutes? About 5 minutes later, that EMB is on your network, transmitting LTE, connected to your core. I mean, when I say it's the lowest barrier of entry, it is as easy as it gets to deploy one of these BiCells. The other cool thing about LTE is that you can actually run these cores redundant. So one question that I get often is, man, what if this device fails? $65 computer, what do you do? Very real concern. You can run these in redundant mode, where you can have more than one. So if one fails, it can fall back to another one. And as we mentioned earlier, it works across the MGMIX. We've proven that out already. So you could put a core in Bibb County, put a core in Chilton County. If the Chilton County one fails, everything falls back to Bibb County, and vice versa. And the users go, man, my speeds are a little bit slower, and that's all they notice. I don't have to rush over there at 2 in the morning. It's nice. And both the Nokia that we have over here and our BiCells gives you that capability. OK, so let's talk about what's next. We do have some limitations of this software right now. Currently, it is natting everything in the name of simplicity. So this is pulling a public IP, and then it nats the customer traffic south of it. Obviously, that's a problem when you're trying to do commercial applications, when you're trying to do the gamers that want that public IP. You are limited to NAT right now in its current configuration. This is a problem I'm actively working on, and we expect to have it patched next month. So right around the bend, we have a solution for that problem. The second thing is that right now, all the installation happens from that command line. I want to take it a step further and make it where you run the command, and then you're done with the terminal. You just immediately move over to the web UI and keep moving. That's our next goal, is that it should be as simple to do this as setting up a Facebook profile, right? In an ideal world, we bring the bar of entry that far down. We also want to do a cloud controller that you can install that allows these to synchronize. So if I enter a SIM card in one, I want it to automatically be put in the other cores. That way, you're not having to sit here and manually put these in across multiple EPCs. We want to make the CLI better, because right now, if you want to make changes after installation, you do have to go into a config file. And these config files are YAML. I personally hate YAML. I know I'll offend half the people in here, but I hate it. YAML is just, I don't like it. It's not elegant to work in. So I want to hide that behind a CLI, and we do have plans to do that in V2. You saw that we can ping the ENBs, so we know the health between our core and the access point. What we don't know yet is the health between our core and the user equipment. And that's also a very important metric to have. We want to expose that, and that's coming in V2. And finally, proactive email notifications. If we have an EMB go offline, we want to be able to know about it without having to leave this portal open and watch the terminal. That's not ideal. We need it going into Slack. We need it going into AI platforms like the one we looked at earlier. We've got to make that where that is easier to get alerts when things go wrong. We haven't had one fail yet like that. But Murphy's Law, now that I've said it, it's going to happen. So we need to expose that functionality and make that bar of entry lower. So that's coming for V2. All right, so hardware. Let's talk about what you need for a basic lab setup. We have 4 things pictured here. We have one of these. This is a ThinkCenter M715Q. Very basic, very affordable thin client. We have our CPE device for our UE right here. That's an indoor global telecom unit. I have to brag on Global Telecom for a second, because they are really an incredible company, and they solve problems you don't think to ask for. For example, your tower misbehaves, and a customer unit goes offline. With some UEs, you need to reboot them, plug them back in for them to get them to come up and reconnect. It's less of a problem if your towers run Nokia, because it just works. But if you're running lower end LTE, sometimes that's a problem. Your tower misbehaves, your customer unit goes offline. The globals have an ability to ping Google, and if they detect that they can't get to Google, they'll just reboot. And they'll keep doing that until they can, which reduces your truck rolls dramatically. If you're changing channels on your tower, adjusting power levels, these UEs have a tendency to go offline. I don't want to drive an hour away to unplug somebody's modem and plug it back in. That sucks. I don't want to do it. So my recommendation is, there's lots of UEs. I'm not going to tell you which one to buy or not to buy, but just buy a global. The globals work. They have outdoor units. They have indoor units. Global is what you want. For your access point, for your RAN, a good starter RAN device is a BiCells Nova 436Q. I recommend this because I don't want you to get demoralized when you deploy your LTE. It's so simple. You plug it in, it pulls an IP address from your network over DHCP. You connect to the IP. You log into this device and you put your packet core IP address in there and you hit save. And then you walk away, fly out the tower, you're done. That's all you have to do to configure the RAN. Way more involved on Nokia. So this is what you want. Nokia is ultimately where you want to go, I think. But when you're just starting out, don't do what I did and start with something hard, because apparently I'm a glutton for punishment. Just buy a 436Q. Tommy, what are these running at last check?
About $4,400.
So $4,400 will get you on new. You can hunt eBay and find them cheaper than that. Because in some places, like that Macaulay Hill example, used hardware, you just need to do that. There's not enough houses to make it make sense unless you don't. So look for deals. Pair that with a KP Performance 65-degree sector antenna. This is a really good company when it comes to antennas. They make good stuff. You're going to want to pair that with your bicells, and then you just need a computer to use as your core. Honestly, any computer, made after like 2012, will do this job just fine. You only need 2 network interfaces on it. Wipe it, put on Linux, and that's your core. I just like these because they're so small and I can mod them. So you technically could even use a Raspberry Pi if you had 2 Ethernet ports on it. You just got to have those two devices, one for your WAN and one for your communication with the LTE components. There are other things not pictured here. This is the big stuff. Like you'll notice that our antenna has ports on it, because you got to be able to connect that antenna to your access point. Okay, so this isn't exhaustive. There are still accessories you need. LTE requires a GPS. You basically have to have it for an LTE network to function. So you'll have to get a GPS. If your unit doesn't have one, you got to get one. You got to have sectors. You got to have the cabling, the fiber cabling to get from that bicells to this. You have to have a router, right? There are just some things that are like obvious in between the lines here. But for the LTE stack, these 4 major things are the main components. But like I said, do research, ask a consultant before buying a bunch of stuff. You don't want a bunch of equipment you can't do anything with. I actually have an example where someone bought Ericsson. Ericsson's an excellent brand, high-end LTE. They bought a bunch of it, couldn't figure out how to program it, so it's sitting on a shelf, which is a travesty. So again, what I'm saying is just because you can buy the top end, it doesn't mean that you should. Start with the bicells, get familiar with it, grow from there. All right.
Yeah, 5 minutes, Josh.
I got it. I'm almost done. I got two slides. OK, so let's talk about now why it actually matters to own and operate your LTE core. The first thing is that you've probably noticed on your phone, if you run a speed test, your phone, when you're connected to 5G or LTE, will say places like Kansas City or Atlanta, even though I'm here in Birmingham. The reason this is that oftentimes these cellular EPCs, these cores, are in major city hubs. So your data has to take a long trip before it could even break out and get to the internet. Okay, this is another reason why when people try to watch, for example, Netflix, or they want to watch the Iron Bowl, War Eagle, they'll end up region locked if they watch it over LTE, because they're hitting an EPC in Atlanta and it thus thinks they're in Atlanta when they're actually in Birmingham. Well, when you own the core, you can put those cores where the customers are, like, oh, I don't know, the cabinet outside their apartment complex. That's magical. The second thing is that if you own the core and you're not going out to the cloud, you can run it offline. This is one of the most incredible aspects of this and why it's so relevant in military and in medical contexts where privacy and security is top tier. The core can run on this box. You can network your devices inside your own private network, and they don't touch the cloud at all. They can be air-gapped. They don't need to get out to the internet. So like technically that bicells can work without one of these with a cloud core, that's what they call it, but that core is way out in a data center somewhere else. You have to be online to utilize it. With one of these, nope, you can run LTE with this box and never go out to the internet. We consider a local core to be what I call a true zero trust environment. I have the picture of this knucklehead with the glasses going nuts over here because that's what most of Silicon Valley is doing right now with your data. They have no respect for your privacy. They log everything. They spy on everything you do. So stop giving them all of this data. Just quit doing it. You have no excuse now. You can build one of these yourself. You can put it in your data center. Don't let crazy man over here see what you're doing. No reason for it. This is what you would use in a utility company setting to telemetry, right? Or military to network your field guys together when they're deep in the forests. LTE can reach them, and their data stays with them. No CCP interference, no Russians, stays right here, safe in America. All right, so moving on to our final slide. I can't end this talk without calling out two people that aren't here, but I wish they were. They are my mentors in this space. They taught me so much. One of them is Mr. David Peterson with 4G Engineer. He took many 1 a.m. calls of me freaking out because I crashed the packet core. Incredible guy. He is one of the most knowledgeable 4G people I've ever met, period. So if you're looking for somebody that really knows this stuff, David Peterson, 4G Engineer, get on Google. He's a great guy. Another one is Mr. Michael Halls, who helped us with PCI. There's a whole lecture we could have about that. We didn't even touch it, but it's part of RAN. And it's important to make your cell sites not talk over each other. It's not something you just know how to do without help. And Michael was instrumental in cutting through a lot of the noise to implement that in our network. So I can't give this lecture in good conscience without shouting out Michael with Nimbus Solutions and David Peterson from 4G Engineer. These two guys are legends. And if they were here, you'd love them. They're super nerds. Lastly, we are looking to duplicate this across the state. This is what I think is going to be the glue that brings AI to the data that it's built on. 4G, 5G is going to bridge that gap. If you need help deploying this in your organization, we're doing this. We can help you deploy one of these. We can help you design a cell site from empty field to fully constructed site and online. We'll even help you get it peered with DMG MIX, right? We're that deep in this. So if you need that help, reach out to us. My email is right here. That's a locally hosted mail server, no Gmail here, josh@lambertmail.xyz. Folks, that's it. That's 5G LTE. So floor's open. Anybody have any questions? I know that was an insane amount of data. So how can I help cut through the noise? Yes, sir, in the back. So that, in an ideal environment, this would be when we're bonding multiple channels together or multiple carriers. So our Nokia AZQCs over here are, yeah, these Nokia AZQCs, you can bond multiple carriers of data together. So these suckers, I mean, I think we clocked 300, almost 400 meg on one of them.
We tested 300 megabit on 3 carrier. We're currently testing 4 carrier. You can do more than that, but on 4 carrier, it's about 100 mega carrier.
And so, and that's again the thing.
On the upload, we've seen as high as about 50, but again, depending on exactly how you're configuring it, you can get more.
But the real game changer on that Nokia site, you saw the core was there in the compound. What that means is that you're getting like fiber latency. When you look at the metrics of that connection, you're seeing 400 by 50 and 18 millisecond ping.
We've seen as low as about 12 and 13 because the core is right there. It's not having to go all the way to the data center and back. It's hitting the bottom of the tower and going right back out.
Yeah, I mean that local breakout is what they call it. And that's why this is so revolutionary and why Open5GS is amazing. You can do that local breakout right there. So you just immediately convert to network where your traditional routing can take you over. And as long as you're paired with a good provider like Unity, again, shout out to those guys, then your customers get just an incredible internet experience. Like it's what makes it work really good. But yeah, to your question, 400, when we do traditional millimeter wave deployment, where we're feeding customers with non-LTE internet at the street level, we've clocked 2 gigabits as our record out there. So it's very, very competitive when you're right there in the right of way beside them. You can solve the challenge without having to dig up everybody's yards. You put one pole, you put, oh, we don't have one of them here today. You deploy something like Tachyon or Ketson, which showed up at the slide earlier today. Ketson and Tachyon are very similar in terms of how they operate. That's 60 gigahertz wireless, and it can do 2.5 gig to the customer. I mean, we're just blistering fast speeds without having to go through all the expense of burying fiber. So a true wireless network, we talked about all the tools in the toolbox. You try to get as many people as you can on your millimeter wave close to them in the right of ways. And then anybody that you can't get on one of those poles, you can put them on LTE. And when you're bonding 3 and 4 carriers on a good platform like Nokia, they're getting 300, 400 meg, and they're happy.
And those are 4G numbers. Those aren't even 5G numbers. 5G is anywhere from 30 to 40% more efficient.
We just haven't made the jump yet. We're still trapped in budget land of deploying 4G, but it's coming.
I don't have it memorized, but I think Dish Network's record is something like 2 gigabit on the downlink by about 500 on the uplink in 5G.
Yeah.
And they were only using, I think, 70 megahertz, so that's really comparable to the 4 carrier we were talking about earlier doing 400 meg.
Yeah, game-changing speeds.
All
right.
I understand you say y'all using CBRS.
Yes, sir. Yes, sir.
You need to mention the SAS.
Yeah, we should. So one of the things that makes LTE deployment unique and different from Wi-Fi, very important consideration, I need to bring this up, is that the spectrum isn't an all-you-can-eat buffet like it is with traditional wireless. With CBRS, we're actually sharing the frequencies with I think it's the Navy, and also what they call PAL holders. So like in the state of Alabama, these are people like Southern Link that have bought access to that spectrum to use it ahead of everybody else in line, right? So what happens is your CBRS devices, this is part of the RAN layer, like that BBU or that bicells, they come up, they connect to a cloud system like Google and say, hey, am I allowed to transmit on these channels? And Google either says, yes, you can, or no, you can't. And that way, you don't just have people broadcasting over the top of licensed users that need that priority access. That's why they call them priority access licenses, so that they are protected. And most importantly, if our military needs that spectrum to kick some butts from people coming in here, they can clear us all out with one command and take it if they need it. So it's a really elegant way of thinking about it, not a perfect system, but it gives you access to 3 gigahertz, which has just insane punch. You can do these 5-mile cell sites that you could never do with traditional wireless.
And the other thing is, he brought up the licensed, but there's also a whole chunk of them, and it's actually over half of it, that is general access that anyone can use.
Yep.
But those licensed channels are also available if the license holder is not using it in the market.
Yep.
So like in Southern Link's case, they bought it basically statewide, but they're only really using it in populated areas. So in these remote areas where we're deploying, their spectrum's actually up for grabs and use because they're not using it.
Yeah. And it's a substantial amount of frequency. I mean, you can do, because there's not that many people using it yet, because they struggle with how to set these cores up, most of our markets, there's like nobody using it. We set up and we get the whole band all to ourselves. And so you can just do these absolutely ridiculous things in terms of speed that would be a much harder thing to do if you're in Manhattan or Chicago, right? But here in Alabama, where we're represented, it really is game changer. It's underutilized, and you should be using this today to connect stuff at the edge. All right, any other questions? Okay, thank you for giving me an audience to preach about LTE. Thank you.